Good morning viewers. I am Dr. S. Chatterji, working as Professor and Head of Electrical Engineering Department, NITA, Chandigarh. Today I am here to talk to you about electric drives. You understand that electric drives are very important so far as the industrial applications are concerned. So, let us see what do you mean by electrical drives. Electric drives, if you have to define it, an electric motor along with its controller and is called the electric drive. Many of the people are confused that electric drive means electric motors. It is not. It is actually the electric motor as well as the control circuit. When you have the combined system, that means you have the motor as well as you have its control unit together, then the whole system becomes electric drives. Modern electric drives, if we want to see, let us see what are the modern electric drive systems which are in use. About 50% of electrical energy is used for drives, fixed speed or variable speed. The drive can be of two types, it could be a fixed speed drive or it could be a variable speed drive. 75% of the constant speed drives are constant speed and 25% are of the variable speed type, that means expanding unit. Variable speed drives typically use PEC to supply the motors, that is it can be a DC motor or it can be an AC motor. So, if you see the DC motors, that is the brushed one, there could be SRM, there could be BLDC, and in AC motors, as you all know, it could be induction motor, it could be PMSM. Now, let us see what is actually the drive. You have the AC system here, you have the AC motor here, you have a fixed speed, that means an axle is there and we connect this AC motor with the DC generator, and there is a control unit here where it will get the variable DC as output, and it goes to the DC motor. The motor will give, DC motor will run at the variable speed and that is accordingly attached with the load. So, the load is getting at different speeds, the load will get different speeds with the help of this DC motor, and they are, some of them are very bulky in nature, they are very not much efficient, quite inefficient and inflexible too. So, this is all about the classic electric drive for variable speed applications. Now, typical modern electric drive systems, let us see what you can have a typical. There is a power electronic converter. Power electronic converters are now these days used for having this control system. The power is get into it, that is power in, then the motor is connected, and further the load is also connected. The whole system becomes a modern electric drive system. Now, if you do not have a controller, it will not work. Controller means you have to have the output which is desired output. If you do not get the desired output, the controller means nothing. So, whatever output you get on the load, you want to get a desired output. Suppose for example, you want to change the speed. So, you have to accordingly change the speed as the motor load changes. So, there is a controller which will have a reference input to it, and further it will go to power electronic converters, and there is a feedback. Now, why feedback is required? This part is the feedback, that means the output of this power electronic converter, here from here we tap the feedback and get into the controller itself. Why do you want it? Because the controller will accordingly sense what is needed for the motor, and accordingly the error, it is compared with the power in, that is the reference input, and accordingly errors are generated and accordingly the speed is varied. So, this is power electronic converters in on the whole. The electric energy unregulated is given, converted with the help of this whole system, and this becomes electric energy regulated, which is used as the output. And this part is the electric motor, this part is the electric motor, this part is the power electronic converters. So, there are two different parts of the modern electric drives. One is the modern power electronic converter, the other is the electric motor. The electric motor has electric energy as input and mechanical energy as output, as it is shown in this diagram. Now, let us see the example on VSD. VSD means variable speed drive applications. if you see, if you have a comparison between constant speed and variable speed drives, you will get like this. This is what is a constant speed drive, and the power is in, power is out, and there is some power loss. This is variable speed drive, means you have speed, speed will be accordingly varying depending upon the load on the system. Power in, power out, and power loss. Power electronic converters in ED systems, converters for motor drives, some possible configurations I have given in this slide. Let us see what are these. DC drives and AC drives. Mainly there are two types of drives which are used in industries. One is the DC drive, another is the AC drive. They have further their classifications as like this: AC source, DC source, AC source, DC source. In both the cases, the source is, it could be AC, it could be DC. AC DC and AC DC DC, AC to DC converter and AC to DC and DC to again DC. Similarly, DC source has DC to AC and then DC, or DC to DC. Let us see about AC drives. It could be AC to DC and then further to AC, or it could be AC to AC, means at different voltage level or at different frequency level. Further, AC to DC and DC to AC can be classified as constant DC and also as variable DC. DC source, if you see, there could be DC to AC, or there could be DC to DC to AC, means the levels are different. So, this is the latest of the devices or the drives, and we call them as smart systems. You know what is a smart system? Smart system is that which has its control. It is an embedded type of control, it is adaptable type of control, and it can work of its own. So, smart sensors, then intelligent controllers, then intelligent actuators, these are the integral parts of the system, and it can control. So, for example, there is a plant, say this a plant on your screen, what you see. You can have smart sensors, you can have intelligent actuators, and suppose a windmill station is like this, you can control this plant with the help of this smartly, that means automatic, more of automation, and it is, that is why also known as intelligent controller. So, DC motors, if you classify, mainly we have separately excited, series, shunt, and compound. These are the ones: separately excited, series, shunt, and compound. So, this is one cut view it has been shown of a DC motor. Speed control options, because I am talking a lot about speeds. Why? Speed is a very, very important factor in industries. There are many processes where you have variable speed. There are certain processes which will have to have constant speed, regulated constant speed, but in many cases the system has to have run at different speeds. So, what are the speed factors? What are the factors which control the speed? Let us see. One is the armature voltage, VA is equal to IA RA. This equation, it is a very known equation, VA is equal to IA RA plus EB, IA RA plus KIF omega, or where omega is equal to VA minus IA RA divided by KIF, or omega is equal to alpha Vs minus IA RA divided KIF, where all you know that IA RA is the armature voltage, armature drop. So, drive speed can be controlled by armature voltage control and field flux control, and this is also known as this field flux control, this is also known as field control. Now, you can very well see from these equations that there are two factors which affect the speed of the drive. One is the armature voltage, another is the flux. Now, here you have to see that if you want to vary the voltage, you can vary the speed of the drive, you can change these aspects, that is armature voltage and field flux control. Now, if you see the characteristic of speed torque characteristic, this is known as, this is constant torque region, this one is the constant torque region from here to here, and this one is known as field weakening. Now, try to understand when voltage is to be varied, when speed for speed, or flux is to be varied for changing voltage. There are two methods, as I said in the last slide. One is the armature voltage control method, another is the field or flux control method. Suppose you want to change the speed from its base speed, this is the one, this is the region where you can change its speed from normal or base speed to within its range. So, our a motor is there which has a speed of say 940 rpm. So, 940 rpm means from 0 rpm to 940 rpm, 940 is known as its basic speed or base speed or normal speed. So, from within this range, if you want to regulate its speed, you have to apply for constant voltage, because voltage, armature voltage is directly proportional to speed. So, if you change the armature voltage, if you increase the armature voltage, the speed is going to increase, and if you decrease the armature voltage, the speed will decrease. It is directly proportional. But reverse is the case for field flux or field control method, where the flux is indirectly proportional to speed. If you want to change the speed, if you want to increase the speed, you have to decrease flux, and as all you know, flux is related with the field current. If I want to change the flux, I have to change the field current. And how can you change it? Field current is directly proportional to flux. You cannot decrease the value of the flux, you cannot increase the value of the flux, you have to decrease it only. And how do you decrease it? By decreasing the field current, by putting a resistance in the circuit. If you want to decrease the field flux, you have to decrease the field current, and that means field flux cannot be increased, it can only be decreased by putting a resistance in the circuit. Now, what is happening? What is the effect? If you are decreasing the flux, since it is inversely proportional to the speed is going to increase. But since you cannot increase the flux, you cannot decrease its speed. So, this field control method or flux control method is mainly used for higher speed uses. Another drive is known as, very commonly known as, which is very commonly used also in industries, is known as chopper drives. These are the units, these are known as SCRs, and these SCRs or triacs, they are being used. These are semiconductor devices, semi controlled rectifier, silicon controlled rectifier or choppers. So, they are being used for making the chopper drives, means you can change the speed of a DC drive by changing its voltage level. You can increase it or you can also decreasing. Mostly in DC drives, it is the chopper is used for decreasing the speed. Now, what is a chopper? Chopper is an electronic switching circuit. As I said, thyristors are used, SCRs are used for this, and which converts the unregulated DC input to a controlled DC output with a desired voltage level. By switching the supply on and off, you can change the level of the DC voltage. Now, what is this switching on and off? Means actually you are changing the on time and also the off time. And if you go for the whole the numerical value of it or the mathematical value of it, you will see that it is nothing but the duty cycle. The duty cycle is meant by two factors, one is T on, another is T off, and if you change T on or T off, you are changing the duty cycle. By changing this value, you can decrease the level of the voltage, and that is why the device is known as chopper. Actually, you are chopping down the DC voltage level. The general block diagram, if you see, this is the DC supply side from rectifier, filter, battery, fuel cell, etc., whatever is your source, and this is the control. This is the derived from feedback circuit, and this is the DC output, and this is the load. Methods of control. The output DC voltage can be varied by the following methods: pulse width modulation control or constant frequency operation, and variable frequency control or current limit control. These are the three methods: pulse width modulation control, which is also known as constant frequency operation, variable frequency control, and current limit control. These are the methods normally used for controlling the speed. Now, what is the pulse width modulation? As I said, you can change, this is the time actually, this is the T on time what I was speaking, this is the T off time. From here to here is T on, from here to here is T off. That is why here you are getting a pulse up to this level, and from here to here, which is T off, you are not getting a pulse. And this total time, that is T on plus T off, is known as T. And if you have T on plus T off, T on divided by T on plus T off, that is T on divided by T, this is known as duty cycle. So, this is known as pulse modulation. You can modulate this by changing either T on or T off. So, duty cycle will change, and accordingly the speed will also change. This is variable frequency control, the second method. So, here also you are changing this as a T on, again you have for this period you do not have any pulse, again you have a pulse here. You can also change it from here to here. So, here the T off period is very small, again a pulse, again T off, again a pulse, and like that. Similarly, here also you are changing it like that, that this is the total time, that is T on plus T off, this is T on, this is T off. Here T on time was more, T off time is less, here T off time is more, T on time is less. So, either way you can change it. So, this is known as variable frequency control method. And finally, what you have is T off, then T on, and then another pulse. So, this is for the T on time when the load is actually energized, you are appearing with the voltage across it, and which we call as load voltage. Now, current limit control, if you can limit the control, also you can change the speed, you can control it. So, this is what is the I max, and this is what is the I minimum. So, from I minimum is this value and I max is this value. So, you change it from here to here, again you change it from here to here, again it. So, you get a T on time like this, T off time is this, again T on time, and this is the total time T. So, you can again change the duty cycle and the control can be obtained. Chopper controlled DC motor. Nowadays, in place of this switching, in place of thyristors, you are also using IGBTs. Okay. So, IGBT is a very efficient drive, very efficient device, and it is mostly used for switching purposes, because its switching time is very less. That is a very efficient and I would say very fast switching device. So, this is the smoothing inductance, as you will know, this is DC motor coupled with that sensor, that is tacho generator many times, because you have to get the feedback, and it goes to the PI speed controller. And here you have a torque reference, regulation switch, and also this reference. And from here you take a feedback, this is known as current measurement, and this is also from current reference. So, you have a controller here which is known as PI current controller, and then accordingly the pulses are given to this IGBT, which is the main controller for further controlling the speed of the DC motor. So, hence you are again changing the level of the voltage, and this is known as chopper controlled DC motor. Quadrants operation. If you see the quadrant operations, you can have all quadrant operations. This is reverse braking, this is first quadrant has forward motoring, second quadrant has reverse braking, third quadrant, this one, has reverse motoring, and fourth quadrant had forward braking. That means all 4 quadrant operations control are possible. So, what are the demerits in this system? Let us see. This system is no doubt a very efficient and very good system, but some of the demerits are here pointed out as bulky as compared to AC counterpart. If you compare it with the AC controller, AC drive, this is a very bulky drive. A commutator sparking, because a DC motor, DC drive has commutator as an integral part of it. So, there has to be some sparking known as commutator sparking, which is not suitable for petrochemicals, mines, chemical application, because there is a fire hazard. So, there this commutation sparking is very I mean it is not desirable at all. So, it is a kind of demerit. Above 500 kilowatt, manufacturing of machine itself is tedious. So, this type of diagram it has been shown to give you an idea what are the armature, commutator, brush, these are the integral parts of a DC motor. So, these are some of the demerits of a DC motor drive. Now, let us see some of the applications. Boiler feed pump, BFP they call it. Boiler feed pump is a very huge pump, and it is used for mostly for thermal power stations and any other place where boiler needs water, boiler needs to be pumped with water, and here this DC motors are applied, DC drives are applied. So, power rating up to 20 megawatt. You can imagine this is a very big motor, very big drive, it can go up to 20 megawatt. Speed ranges from 3000 to 6000 rpm, and rated system conditions are 170 bar, 2465 psi, and 565 degree Celsius it can bear. Electric cars, again a very important application, wherein you can have lot many such drive controllers, and these are also You know, these days we have cars, these are the ones, this slide shows this. This car, you can just get it charged at the stations. There are charging stations available. Well, in India we do not have such systems now, but they are going to get it introduced very soon. In abroad, in foreign countries, mostly this type of arrangements there, which you can go and charge your car and then you can use it also. Then electric car speed control. There is a wonderful arrangement like this. This is the DC controller, this is the battery of some 96 volt and the DC motor and you get a pulse like this, pulse train like this, and thousands of pulses per second can be obtained by such a system, and this is meant for electrical speed control. Electric bikes, another application. Lot many bikes are there which have this type of controllers. These are the bikes, for some of them are shown in this slide, and these are with the help of your DC motor drives. Electric trains and trams. You know, Calcutta is one of the places in the country wherein you have trams like this. You have electric trains everywhere, of course. This is one which is shown in the foreign countries. In India also, in Delhi you have metro, in Kolkata also you have metro, and this is an electric drive. So, they also use electric trains and trams, these type of drives. Paper mills, lot many application of DC drives in paper mills, because paper mill has one thing, kiln is also used, which needs to be used at a very small speed, 6 rpm, 8 rpm, 10 rpm, something like that, and therein you use such type of drives. Steel rolling mills, this is another application. Lot many DC drives controllers are being used in steel rolling mills. Lifts, as you all know, lifts and your hoists, they are using DC motor drives, DC control drives. Hoists, as I said, these are the hoists. If you go to any industry, you will find such hoists are there, and you know there is a small controller in the hand of the operator. He can just operate that and control it in all angles. You have lot many degree of freedom. You can take it further, you can take it back, along, high, low, etc., etc. So, this is one very important application called hoists in industrial industries. Then power electronic converters in ED system. Power electronic converters in ED systems are, you have the diagram is like this. You have a 3-phase supply. Okay, this diagram is meant for a thyristor drive, and this is also a thyristor drive, but which is actually converting it into AC. This is a thyristor rectifier, and this is an inverter. So, DC drives are AC to DC. So, 3-phase supply is there, which is rectified, further it is controlled and the motor is controlled with it, and then finally it is inverted. So, 3-phase AC supply is also available here. So, these are some of the equations which you can work out mathematically, and the important part of it is that you have quadrant 1 control, quadrant 2 control, quadrant 3 control, quadrant 4 control, omega versus T. You can always have this type of controllers, are very useful for industries. One thing I would like to mention, that if you are using a thyristor bridge, actually this is a thyristor bridge, this is also a thyristor bridge, but this is used as a rectifier mode and this is used as an inverter mode. Now, what is the basic difference? Same thyristor is being used, the only thing is the configuration is different. This thyristor rectifier will have to be triggered or conducted at an angle less than up to 90 degrees, means 0 to 90 degree. If the firing angle or the triggering angle is 0 to 90, the configuration bridge, the 3-phase thyristor bridge will work as a rectifier, and if you go beyond it, then it works as an inverter, that means more than 90. So, let us see what is happening this quadrant 1. Quadrant 1 means this side is positive, this side is also positive. If you take voltage and current IV characteristic, the power will be positive. Positive into positive means positive. So, here it is always a rectifier mode, because the power is positive, because it is drawn out of the supply. But what is happening is quadrant 2, the voltage is positive, but the current is negative. So, current negative means the power will be negative. So, negative power means it is actually not taking any power from the supply, but it is feeding power to the supply. So, it becomes an inverter mode. That is why it is it is a double bridge configuration. One is a thyristor rectifier, another is a thyristor inverter. The inverter is supposed to have its configuration differently than thyristor, this rectifier bridge, and this can always supply 3-phase supply to the power system. So, this is the beauty of the system. Power electronic converters in ED systems, let us this is a DC drives, AC to DC, means cascade control structure with armature reversal, again 4 quadrant control can be used. So, these are the thyristors I have shown. This is a 3-phase thyristor bridge and this is the motor, here is the supply, and when you trigger them and change their firing angle, you can change the speed here. So, this is known as power electronic converter and the control is basically a power electronic controller. So, this is the block diagram, you have speed controller, you have a reference, I mean the comparator, you have current controller, you have firing circuit and you have armature reversal. So, this type of arrangement you can have, and you can have power electronic converters for ED systems. Modeling and control of electric drives. Let us see what is modeling of the power converters. Induction motor drives. Induction motor drives can be like this, the scalar control and the vector control. You know that scalar control and vector control means the direction also has to be there. In scalar only the physical quantity is there. So, scalar controller can further be classified as constant V by F control, V by Hertz means V by F control, very popular controller, and here is the equation for current, and the vector control is FOC and DTC. So, there is direct torque control and is flux of control. FOC can further be classified as rotor flux and stator flux. You have 2 types of flux, one is in the rotor, what is known as rotor flux, there is another flux in the stator which is known as the stator flux, and DTC can be further classified as circular flux, hexagonal flux and DTC SVM. So, this is what is the induction motor drives. The AC drives, what are these drives? AC motor drives are used in many industrial domestic applications such as in conveyors, lifts, mixers, escalators, etc. The AC motor drive have a number of advantages. They are very light in weight, 20% to 40% lighter than equivalent DC motors. DC moters were one basic demerit or disadvantage of DC motors were it was very bulky and it was taking lot of floor area also, space also it takes. Here it is lightweight, as I said it is 20% to 40% lighter as compared to equivalent DC. Same rating if you have, this is 20 to 40% lighter. Similarly, the space required is lesser. Inexpensive, this is much inexpensive as compared to DC drives, and low maintenance. It requires very low maintenance, so maintenance cost is reduced. The disadvantages of AC motors, these are the advantages, and let us see the disadvantages. The power control relatively is complex and more expensive. The control part, the motor part is the advantageous part, but if you see from the whole drive, that is the control part along with the motor, the power control, the power unit and the control unit. There are 2 units, one is power unit, another is control unit. So, control unit relatively is complex and more expensive as compared to DC drives. There are 2 types of AC motor drives, one is induction motor drives, the another is synchronous motor drives. Let us see. Induction motor drives, it is like this, the 2 main basic parts are stator and rotor, as you all know. This one is rotating, so it is known as rotor, and this one is stator, static in nature, that is known as stator. 3-phase induction motors are commonly used in adjustable speed drives, ASD they call it. Basic part of 3-phase induction motor is like this, the 3-phase windings, this is the stator side and this is the rotor side. Rotor winding and stator, you give a 3-phase supply, this 3-phase winding, when you give a 3-phase supply, as you all know, a rotating magnetic field takes place. That means this magnetic field, what is formed here, it is rotating in nature, and as you all know, there is the air gap between these two, and this magnetic field is rotating at a synchronous speed, omega s is synchronous speed, and then this magnetic field, when it cuts the rotor winding also, there is another mutually induced EMF in this rotor part, rotor winding, which is also 3-phase in nature, and this rotates at another speed omega m. Now, there cannot be same speed between the two stator rotor air gap as I have shown, because the stator field rather is rotating at a speed which is known as synchronous speed, and the synchronous speed as you all know is given by 120 f by p, where f is the frequency and p is the number of poles. So, number of poles, if number of poles are 2, so it becomes a 3000 rpm synchronous speed. So, rotating field is rotating, a stator field is rotating at a speed of 3000 rpm. Rotor magnetic field is also trying to rotate because of mutual induction, but if these speed are same,